look over at the wall of your living room right now, or, out the window, and just find your air conditioner.
Yeah, that boring, humming white box.
Exactly. It just feels like the absolute definition of benign domesticity, right? We treat it like a fancy fan. You point a remote at it, press a button, the room gets colder, and you just go about your day.
It's completely invisible to us.
Right. But if you peel back the plastic casing of modern refrigeration systems, the reality of what is actually sitting in your home is, frankly, genuinely shocking.
Oh.
You are no longer looking at a simple fan. You are looking at a highly engineered, surgically controlled environment, circulating actively explosive gases.
You really are. It represents a massive, almost completely invisible paradigm shift. I mean, the appliances we just take for granted have gone from utilizing these chemically stable, totally inert substances to, well, operating as highly managed hazard zones.
Yeah.
And this transition is happening right now in almost every domestic space on the planet.
Which is wild.
Yeah.
So welcome to the deep dive. Today we have a really fascinating stack of technical guidelines from the UN Environment Program. Specifically, we're looking at it's a fast-paced but very dense manual titled Good Servicing Practices for Flammable Refrigerants. And our mission today is to uncover the incredible high-stakes science hidden inside that machine that cools your bedroom.
Yeah. And to really appreciate the urgency of this manual, we have to look at the massive disruption sweeping through the RAC industry. That's refrigeration and air conditioning.
Right.
Because for decades, the global standard was this refrigerant called R22. And from an engineering standpoint, R22 was like a dream.
Oh, absolutely.
It's chemically stable, practically impossible to set on fire. I mean, the fatal flaw was entirely environmental.
Yeah, it was actually tearing a hole in the ozone layer.
Exactly, and trapping immense amounts of heat in the atmosphere.
So manufacturers were basically forced to pivot to combat that catastrophic environmental damage. They started phasing out those old refrigerants in favor of alternatives with an ultra-low to medium global warming potential.
Right, the GWP.
Yeah, and just to define that jargon for a second, global warming potential, or GWP, is essentially a score of how much heat a greenhouse gas traps in the atmosphere compared to carbon dioxide.
Right.
So the goal was to find gases with a very low score. And they landed on alternatives like R290, which is straight up propane.
Literally just propane.
Literally. And R600AA, which is isobutane. And a newer gas called R32. But introducing these ultra-low GWP chemicals comes with a massive, terrifying catch.
They are highly flammable.
Highly flammable.
This is the trade-off, To save the atmosphere, the industry had to introduce flammable, potentially explosive chemicals into the living rooms, bedrooms, and offices of millions of people.
Which means the box cooling you down right now is performing a very, very delicate chemical dance. So today, we are going to learn how the unsung heroes of this transition, the servicing technicians, managed to keep us perfectly comfortable without, accidentally blowing up our houses.
Right, because servicing these units requires the staggering combination of theoretical chemistry, rigorous spatial mathematics, and honestly, intense physical discipline.
So let's start with the chemistry, because to understand how technicians avoid disaster, we first need to understand the precise nature of the danger itself. It all boils down to knowing the exact tipping point of when these gases will catch fire.
Exactly. And the UN manual relies really heavily on the ISO 817 safety classifications.
Okay.
You can think of this as the International Warning Label System for refrigerants. It categorizes every single gas based on two specific vectors, toxicity and flammability.
Right.
Toxicity is straightforward and it gets a letter grade, so A is for lower toxicity, B is for higher toxicity.
I think so.
And then flammability gets a number scale. 1 indicates no flame propagation at all. 2L means lower flammability, 2 is solidly flammable, and 3 designates higher flammability.
Okay, let's unpack this. The old baseline, R22, was an A1, right?
Yes.
Low toxicity, no flame. You could basically bathe in it and be totally fine.
Pretty much.
But the new environmentally friendly gases are a completely different story. The guide classifies R290 propane as an A3, highly flammable.
Very high.
And R32 is classified as an A2L, meaning it has a lower flammability, but under the right conditions, it will still absolutely ignite.
Yeah, and technicians have to memorize the specific behavioral quirks of each of these classifications. They focus acutely on what chemists call the flammability range.
The range.
Right. And this range is defined by two absolute boundaries. the LFL, which is the lower flammability limit, and the UFL, the upper flammability limit.
Okay, so imagine you are trying to light a backyard gas grill, right?
Check.
If you barely crack the dial open and just a tiny microscopic trickle of gas mixes with a rushing wind, clicking the igniter does absolutely nothing.
Right, no fire.
Because the mixture of fuel to air is too lean.
Yeah.
You're below the lower flammability limit. Now imagine the opposite extreme. You leave the gas flowing with the lid closed for 10 minutes, just flooding the entire enclosed space.
Oh boy.
There is so much gas in there that it has basically pushed all the oxygen out. Clicking the igniter still might not do anything because the mixture is suffocating itself.
Oh, exactly.
That is being above the upper flammability limit. The mixture is too rich in vapor or too starved of oxygen to actually burn. So the absolute danger zone is the exact, perfect Goldilocks mixture sitting in between those two extremes.
And what's really fascinating here is how narrow and unforgiving that Goldilocks zone actually is.
Yeah.
Yeah. I mean, for propane, the lower flammability limit is just 2.1% by volume in the air.
Wait, 2.1%.
Just 2.1%. If just 2.1% of the oxygen in a localized space is displaced by propane vapor, you have crossed into a highly explosive environment.
That is a disturbingly small amount of gas to become lethal.
It really is. And it doesn't even always require a physical spark to set it off.
Right, because the source text brings up that terrifying metric called the auto-ignition temperature.
Yeah, auto-ignition. This measures the lowest possible temperature at which a specific refrigerant will spontaneously burst into flames in a normal atmosphere, purely from ambient heat.
No open flame.
No open flame, no electrical arc, just heat. For R32, that spontaneous ignition happens at 648 degrees Celsius.
Okay, pretty hot.
But for propane, it happens much lower at just 450 degrees Celsius.
Wow. So if we connect this to the bigger picture, the technician's entire existence revolves around managing the classic fire triangle, right? Heat, fuel, and oxygen. All three must be present for combustion.
Absolutely. And oxygen is an unavoidable constant in a human home. You can't get rid of it. Right. So the refrigerant serves as the fuel. And everyday household items provide the heat or the ignition. The technician's core directive is ensuring the fuel never reaches that 2.1% threshold while exposed to the air.
Which sounds totally simple until you remember that these appliances live in people's wildly unpredictable homes.
Right.
You can't control the oxygen, you can't always control the heat sources. So you have to ruthlessly control the fuel.
Exactly.
How do we guarantee the gas never hits that lower flammability limit in your specific living room? This is where the chemistry basically translates into strict life-saving mathematics.
Yeah, it becomes pure math. The UN guide introduces a mandate known as charge limitation.
Charge limitation.
Right. This is the maximum legally allowable quantity of a flammable refrigerant that can be introduced into a specific room.
Okay.
A technician cannot just rely on intuition or a generic gauge to decide how much gas a unit needs anymore. They are bound by a rigid mathematical formula to calculate a variable called max.
Yeah, the formula in the UN manual looks like something out of an advanced physics exam.
It's intimidating.
Very. But we don't need to do the actual arithmetic to understand its impact here. It essentially calculates how much gas a room can safely swallow if the entire AC unit were to violently rupture and empty its contents all at once.
Right, worst case scenario.
Exactly. It weighs three main constraints: the baseline flammability of the specific gas, the physical size of the room, and most surprisingly, how high up on the wall the AC unit is mounted.
Yeah, the height factor. And applying that formula to a real-world scenario from the manual shows just how drastically the math dictates reality.
Give me an example.
Let's say a technician is installing a standard wall-mounted unit in a completely average 30-square-meter living room. If that AC runs on R32, that's the A2L lower flammability gas, the formula allows the technician to charge the system with a maximum of 5.63 kilograms of refrigerant.
Okay, 5.63 kilos. But watch what happens if the homeowner purchases an eco-friendly unit that runs on R290, which is propane. If the tech tries to install that propane unit in the exact same 30-square-meter room, the legal limit aggressively plummets. The maximum allowable charge for propane in that space is just 0.41 kilograms.
It's a massive drop, a drop from over 5.5 kilos down to less than half a kilo.
That is a severe restriction.
And that restriction is entirely because propane's lower flammability limit is so much more volatile. It takes significantly less propane to build a bomb in your living room, so the quantity of fuel allowed in the machine is aggressively capped.
Here's where it gets really interesting, though. Let's look at the height variable in that formula. designated as HE0.
Oh, yeah.
The manual provides wildly different numerical values depending on the physical location of the machine. The number is incredibly low if the AC is sitting on the floor, it's slightly higher for a window unit, and highest if it is mounted flush to the ceiling.
Right.
Why does the math change based on the physical altitude of the plastic box?
Well, the answer lies in fluid dynamics and the physical mass of the molecules. These newer flammable refrigerants, particularly the hydrocarbon family like propane, are significantly heavier than the surrounding air.
Heavier than air?
Yes. So when a leak occurs, the gas does not float upward and peacefully dissipate into the atmosphere.
It falls.
It falls. It rapidly sinks toward the ground, and it just pools there.
Like invisible water overflowing from a bathtub, just filling the room from the bottom up.
That is an excellent way to visualize it. If a floor-mounted unit springs a leak, all of that heavy gas immediately pools at ground level.
Right.
That is the exact level where pets sleep, where people walk, and crucially, where common ignition sources live.
Oh, wow.
Baseboard heaters, floor-level electrical outlets, or even, the static electricity from walking across a rug in your socks.
Just a tiny spark.
Right. Because the invisible puddle of gas is concentrated down there, it reaches that lethal 2.1% flammability threshold almost instantly in that localized space.
That is terrifying.
But if a ceiling unit leaks, the heavy gas has to travel down through several feet of ambient air, diluting and scattering as it falls. By the time it reaches the floor, it is far less concentrated.
Oh, I see.
Therefore, the safety threshold for a floor unit is mathematically much stricter than for a ceiling unit.
That is just brilliant engineering. I mean, the math isn't just about the raw cubic footage of the room. It is predicting the physical behavior of an invisible hazard over time.
Exactly.
And this logic operates in reverse, too. The manual details the concept of minimum floor area. So if a manufacturer states that a specific propane AC requires exactly 1 kilogram of gas to function, the technician must calculate if the room is legally large enough to absorb a total leak of that 1 kilogram.
Right, they have to do the math first.
Yeah, and if the bedroom is too small, they have to pack up their tools and leave. They cannot legally install that machine.
Which raises a really important question. The math sets the boundaries, the variables are calculated, we know the limits, but eventually a physical human being has to maintain this appliance. What happens when a valve breaks? How does a technician safely open a pressurized system full of explosive fuel while standing inside someone's home?
Right, because if the math is this unforgiving, the physical process of repairing the machine must be incredibly tense. This brings us to the final piece of the manual, the technician's arsenal.
Yeah.
Because you are deliberately breaking the sealed environment.
Yeah.
You're exposing the flammable fuel to the oxygen-rich air.
And the UN manual outlines a draconian set of rules for this exact scenario.
Draconian is a good word for it.
Before a single wrench is turned, the technician must establish what is called a temporary flammable zone.
A temporary flammable zone.
Right. This mandates a completely clear, secure radius of at least 2 meters in every direction around the appliance.
Okay, so practically speaking, what does that look like in a listener's home? Are they, like, moving the couch?
Yeah.
Unplugging the flat-screen TV? Kicking the golden retriever out of the room?
All of the above. Every single potential source of ignition within that 2-meter sphere must be physically neutralized.
Wow.
That means unplugging lamps, removing space heaters, ensuring no one is smoking in the adjacent room, and yes, removing pets that could generate static or knockover equipment.
It is essentially establishing a surgical quarantine zone in your living room.
It really is. And even bringing the replacement gas into the house involves intense protocol.
How so?
Well, the manual explicitly states that technicians can never store more than 50 liters of water capacity equivalent in a residential premise.
Okay, let's translate that jargon for a second. Water capacity equivalent doesn't mean the weight of the gas, right?
No, not the weight.
It refers to the physical interior volume of the metal cylinder itself, as if you were filling it with water.
Exactly.
So you can't just wheel a massive industrial tank of propane into someone's hallway.
Definitely not.
And there are strict behavioral rules for those smaller cylinders, too. They must be kept perfectly vertical, never rolled across the carpet, shielded from direct sunlight through windows, and under zero circumstances can they ever be stored in a basement.
Yeah, and that basement rule is a direct reflection of the fluid dynamics we discussed earlier.
Invisible water.
Right. If a cylinder valve fails in a basement, that heavier-than-air gas floods an enclosed subterranean space with zero natural ventilation.
Oh, man.
The heavy vapor simply pools on the basement floor, just silently waiting for the home's water heater or furnace pilot light to kick on and provide the spark.
It is a terrifying mental image. So,
Oh.
okay, the room is quarantined, the heavy gas is managed. Now, the technician actually opens their toolbox,
Yeah.
but the UN guide makes it abundantly clear that a standard handyman's toolbox is a death trap in this environment.
Oh, yeah. And this is the most difficult adjustment for veteran technicians who spent 2 decades casually working on non-flammable systems.
Because they're just used to doing it a certain way.
Exactly. Standard tools are inherently dangerous here. A
Yeah.
battery-powered hand drill, a heat gun, even something as benign as a domestic hairdryer used to speed up defrosting.
Right.
The text strictly outlaws them.
Wait, surely they still need a heavy-duty drill to access wall panels, though.
A standard drill is essentially a handheld spark factory.
Really?
Yes. The tiny continuous electrical arcs generated by the motor inside the plastic casing of a drill are more than enough to ignite a localized pocket of propane vapor.
That's crazy.
Every single piece of equipment must be highly specialized and explosion-proof. They use specialized ventilation fans to continuously clear the air, but the electrical switch for that fan must physically reside outside the 2-meter flammable zone.
So the simple act of flipping the switch doesn't spark an explosion.
Exactly.
Wow. And the most complex tool in their arsenal is the vacuum pump. To properly prepare the copper pipes for the new refrigerant, they have to remove all the ambient moisture and air from the system.
They do.
The manual states they need a specialized 2-stage vacuum pump, capable of pulling a vacuum to 200 to 500 microns.
Which is incredibly deep.
Yeah, a micron is a microscopic measurement, a millionth of a meter. We are talking about aggressively sucking out the atmospheric pressure until there's virtually no physical matter, oxygen, or moisture left inside those pipes.
And the critical warning in the text is what technicians absolutely cannot use to achieve that vacuum.
Okay, what is it?
Historically, some technicians would cut corners by using an old standard reciprocating compressor, like the motor salvage from an old refrigerator, to act as a makeshift vacuum pump.
Oh, I've seen people do that.
The UN guide forbids this with extreme prejudice when handling flammables.
Wait, why is an old compressor so dangerous? It pulls air just like a pump, right?
It pulls air, yes, but it wasn't designed to operate in a deep vacuum while surrounded by flammable vapor.
Ah.
Standard compressors have internal electrical relays and motor windings that are exposed to the gas flow. When you pull a deep vacuum, you remove air resistance.
Okay.
Without that air resistance, the electricity behaves differently. Sparks and arcs between the internal motor windings can actually jump further distances.
Oh, wow.
So if you use a standard compressor to pull a vacuum on a system that still contains trace amounts of explosive gas, you are practically guaranteeing an internal arc and a subsequent explosion.
That makes total sense. The guide also hammers home the absolute danger of mixing chemicals.
Yes.
You can never take an old, broken AC unit designed for the safe, non-flammable R22 gas and simply retrofit it by pumping in the new eco-friendly flammable gas.
Right, because the internal architecture of the old machines, the electrical relays, the seals, the contactors, were never designed to suppress sparks or handle volatile hydrocarbons.
Right.
Upcycling an old machine with new gas is a recipe for a catastrophic failure.
A literal pipe bomb.
Essentially, yes. And when technicians are removing gas from a system, they must use specific, highly rated recovery cylinders. They can never use cheap disposable tanks.
Makes sense.
Even then, those heavy-duty recovery cylinders can only be filled to 80% of their water capacity to allow for the natural heat-induced expansion of the gas.
So what does this all mean for the moment of truth? The repair is done. The new gas is in. The technician needs to double-check their work and ensure the system isn't leaking an invisible hazard into your bedroom. Can they just grab their trusty electronic leak detector, wave it over the copper pipes, and wait for a beep?
Absolutely not. And this is perhaps the most life-saving detail hidden in the entire manual.
Really?
Standard electronic leak detectors, the exact same diagnostic wands technicians have safely relied on for decades to detect HFC gases, are fundamentally blind to hydrocarbons like propane or isobutane.
Wait, blind? Like the sensor just doesn't register the chemical at all?
Correct. The sensors are tuned to a completely different chemical signature.
Oh, man.
So if a technician mistakenly brings their old, reliable leak detector to service your new propane AC, that wand might glow green and remain completely silent, indicating the room is perfectly safe, while the technician is actively standing inside a highly concentrated, invisible cloud of explosive propane.
That's terrifying.
It really is. The reliance on newly calibrated, specialized hydrocarbon leak detectors is absolute.
That is genuinely chilling. The margin for error is non-existent.
Again.
And what about the oldest trick in the plumbing book? Can they check for leaks using a tiny open flame to see if it flickers?
The manual issues a massive bold print warning against this, particularly regarding the A2L gas R32.
Okay. Obviously, introducing an open flame to a highly flammable environment risks a concussive explosion.
Right, that's the obvious one. But R32 presents a secondary, highly toxic threat.
What is it?
If R32 gas is exposed to the high heat of an open flame, it undergoes a severe chemical reaction that produces hydrogen fluoride.
Hydrogen fluoride. The name alone sounds malicious. Why is it so dangerous?
It is an incredibly toxic and highly corrosive gas. If inhaled, it attacks the lungs and respiratory system aggressively.
Oh, wow.
So a careless technician using a flame to hunt for a leak doesn't just risk blowing out your living room windows, they risk silently filling the space with a highly corrosive, poisonous chemical cloud.
Well, this has been an incredibly eye-opening journey. Let's pull all these threads together. What the UN manual reveals is that the modern air conditioner, that entirely forgettable white box mounted on your wall, is actually a masterpiece of high-wire environmental science, chemistry, and precision engineering.
It really is. The global pivot toward ultra-low global warming potential gases is an absolute necessity for the survival of our climate.
Right. We had to stop using chemicals that trap heat in the atmosphere.
We had to. But that noble environmental goal has quietly transformed routine AC maintenance into a high-stakes tactical operation.
Yeah.
It demands uncompromising safety protocols, strict mathematical adherence to spatial charge limits, and a completely reinvented arsenal of specialized explosion-proof technology.
So to you listening, the next time your home feels a little warm and you call a technician to service your AC, you should observe them with a profound, newfound respect.
Absolutely.
They aren't just topping up the Freon like it's windshield wiper fluid. They are meticulously calculating fluid dynamics.
Sure.
They are actively managing a temporary flammable zone right next to your television.
And using complex vacuum pressures to ensure that the fire triangle never has a chance to complete itself inside your home.
It is a brilliant testament to human adaptability, really. We have figured out how to take highly volatile, actively explosive chemicals and safely domesticate them to keep our living spaces perfectly comfortable while simultaneously protecting the global atmosphere.
But that delicate balance only exists because of the rigorous, invisible discipline of the technicians doing the work.
Exactly. It makes you look around your living room a little differently. Which leaves us with a lingering question to ponder. As we rapidly upgrade our infrastructure to be more climate-friendly, prioritizing unprecedented efficiency and new materials, what other quiet, deeply familiar everyday appliances in our homes are secretly undergoing radical, potentially dangerous chemical transformations right under our noses, just waiting for their own deep dive?
It is a fascinating thought experiment for the next time you turn on your induction stove or open your smart fridge or plug an advanced eco-friendly device into the wall.
And as you sit there on your couch, listening to the gentle rhythmic hum of your air conditioner, you can appreciate not just the wave of cold air hitting your face, but the invisible, meticulous mountain of science actively keeping you perfectly safe. Thanks for listening.